Okay, we can add matrices, we can multiply them. There's actually an algebra of matrices that acts a whole lot like the algebra of real numbers. Okay, so let's just look at one operation. You can add matrices. So matrix addition behaves just as you would expect. Okay, now what would you expect? Well, if I add two matrices, first place, how do we define addition? Well, we take the 1, 1 element of the matrix and we add them. That's the 1, 1 element of the new matrix. 2 and 6 goes here, 3 and 7 goes here, 4 and 8 goes here. Now we can't add matrices unless they have the same number of rows and columns, because every number in every row and column in one matrix has to be matched by a number in the same row and column in the other. So if the dimensions of the matrix are different, you can't add them. Okay, well, anyhow, this addition ends up, and that's very trivial. Okay, if you reverse the order, you get the same result. Okay, so obvious, if I switched and did the 5 plus 6 plus the 5, 6, 7, 8 plus the 1, 2, 3, 4 matrix, well, I'd get 5 plus 1, 6 plus 2, 7 plus 3, 8 plus 4. I get exactly the same sums, but in different order. And since the sum of two numbers doesn't depend on the order in which you add them, the sum of two matrices doesn't depend on which order in which you add them. So the matrix addition inherits the commutative property from the real numbers. And we can state that property as A plus B equals B plus A for any matrices A and B. Now, there are all kinds of caveats and conditions, and your book will give you those. And you want to pay attention to them because they're actually important. There are many different algebras around, and you might well encounter other algebras other than matrix algebra. Okay, you want to understand that addition or something analogous to addition, commutative laws, so forth, are important. Okay, well, there's another thing. If you add 0 to any number, you just get that number. Okay, adding 0 to a number doesn't change it. Well, adding the 0 matrix to a matrix doesn't change it, and it's pretty obvious why this is. If you understand how to add them, you're adding 0 to every element, and that's not going to change any of the elements. Okay, so we can say that the 0 matrix plus the A matrix equals the A matrix plus the 0 matrix equals A, where 0 stands for the 0 matrix. This is a 0 matrix, and this is going to stand for the 0 matrix. Sometimes we've got to put subscripts in the 0 matrix. This would be like 0, 2, 2, because it's a 2 by 2 matrix. So we could have another 0, 0, 2, 3 would be a matrix with 2 rows and 3 columns, okay? We sometimes have to make that distinction because those two matrices are different. They have different numbers of rows and columns. And when it's necessary to do that, you do that, and your book will tell you that. Okay, we can multiply a matrix by a number, just as we can multiply a number by a matrix. We multiply a matrix by a number, and we get this. We could also multiply by 3 by any number, and we just multiply every entry of the matrix, every element of the matrix by that number. And it doesn't matter if we multiply by 3 on the left or the right, it comes out the same. Okay, well, that's matrix addition. I haven't proven anything, so you have to prove it more generally, and you got to use IJ notation, it gets a little tedious, but it's not difficult to write out the proof. Okay, that's matrix addition. Now there's matrix multiplication. So you know how to do matrix multiplication. And one thing about matrix multiplication okay? It's not commutative. Now, in your work and in your exercises, you're going to verify this for a couple of matrices. You can just write down any two different matrices and multiply them this way, and then multiply them backwards, switch the matrices, and you're going to get different results. Okay. Just about any matrix, any pair of matrices. But one property, now that both well, a little more about multiplication, okay? Multiplication by the identity matrix, okay? We'll just use the 1, 2, 3, 4 matrix. Now you can do this in your head. It's obvious this is going to give you, and if you don't see it immediately, stop and think about it until you do. It's going to give you this. And uh, 1, 2, 3, 4 times the 1, 0, 0, 1 matrix also gives you the original matrix back. I'll use a subscript here. 1, 0, 0, 1 is I2, the identity matrix of dimension 2. I3 would have 3 rows and 3 columns, and the numbers in the diagonal would all be 1s, and the other numbers would all be 0s. And you want to convince yourself that that works. Okay. So here's one matrix that commutes with any matrix on multiplication. Okay, this is the identity. Any identity matrix multiplied by a compatible matrix equals that matrix multiplied by the identity equals itself. Okay, so that's your identity. Just do a few multiplications. That's easy to understand. Now, here, this is not usually equal to this. Matrix multiplication is not commutative. Again, you can verify that. Just make up almost any two matrices, pick a couple of these ones. Multiply them in one order, multiply them in another order. You're likely not to get the same thing, unless one of the matrices happens to be the identity. Okay, so there's another important algebraic property. It's the associative property. Okay, multiplication is associative and addition is associative. Okay, so you could say that A plus B plus C. Now, if you got 3 matrices, A, B, and C, you add B and C, and then you add that to A. That's the same as if you add A and B and then add that to C. Similarly, if you're multiplying 3 matrices, A multiplied by BC equals AB multiplied by C. Now this takes a little more work to prove. This one is really obvious because this just gets inherited again from the associative property of real numbers. This is a little more subtle, a little harder to prove. But you can verify it yourself and you'll see examples and you'll probably be asked to verify an example of that. And you can expect at any point of the course to be asked to at least verify that matrix multiplication is associative, but not commutative. Okay, well, those are important algebraic properties, and there's more. So we'll switch boards out and then we'll pick up with a little bit more. Okay, so there are inverse properties, okay? And they're a little different. They're not really much different than inverse properties you get for real numbers. So for example, for real numbers, a plus negative a equals 0. Okay, so that means you have additive inverse to any real number. For any real number, you can add it to its negative, you're going to get the identity. Okay, a and negative a combine to yield the identity. Similar, if A is a matrix, A plus negative A is equal to the 0 matrix. For example, again, let's just use 1, 2, 3, 4. It doesn't matter what numbers you put into the matrix or how big you make the matrix. This one's easy to write down, easy not to get confused. Negative A means negative 1 times A, which is negative 1 times 1, 2, 3, 4. And it's easy to see that's negative 1, negative 2, negative 3, negative 4. And A plus negative A equals 1, 2, 3, 4 matrix added to the negative 1, negative 2, negative 3, negative 4 matrix. And it's easy to see that that's equal to 0, 0, 0, 0, the additive identity matrix. Okay, so 0 is the additive identity. And this 0 matrix is the additive identity for matrices. Now, a minute ago, I said that the I, the one with the ones in the diagonal, was the identity. It wasn't being very specific. That's the multiplicative identity. Okay, this is the additive identity. We usually don't talk much about the additive identity matrix, but the multiplicative identity matrix is central in so many ways to the theory of matrices and the applications. It's hugely important matrix. Not that this is unimportant, but its properties are pretty simple. Properties of the multiplicative identity matrix, or the properties around the idea of the multiplicative identity matrix, are a little more complicated. Okay, so these are additive identities. Okay, so I could put a little heading here, additive identities. Okay, over here, make sure it can be seen here, multiplicative. I said additive identities, multiplicative inverses. Okay, so for real numbers, if A isn't equal to 0, then A times the reciprocal of A, which could be written as A times A to the negative 1, or the inverse additive multiplicative inverse of A, equals 1. That's familiar from the real numbers. It's a little more complicated when we do this with matrices. So I'll say for most matrices, A there exists a unique matrix A inverse. I say most matrices, I've got to be careful, most square matrices. By square matrix, I mean one that has an equal number of rows and columns. I could say for most n by n matrices, where n could be any counting number. Okay, so anyhow, for most square matrices A, there exists a unique matrix A inverse such that A multiplied by A inverse is the identity. Now, if I said n by n matrices, then A by A inverse would equal I sub n, but it's clear that when you multiply two square matrices, you get a square matrix of the same size. If that's not clear to you, think about it a little bit. So we have this, that's the inverse matrix. Now, how do you know which matrices? Because for some matrices, I say for most matrices, okay? I'll say this is so. Provided A reduces by Gauss-Jordan reduction to the identity. The matrix, ones in the diagonals, zero everywhere else. Okay. And if not, it ain't so. That is, you can't find an inverse. Okay, so you can find an inverse exists, the inverse exists if, and only if, A reduces to I. Okay, and a little terminology. I don't think it's necessarily introduced here, but I'm going to introduce it now because it's a good time to make sense of the word. I'm going to change this. If A has no inverse, well, that means that it doesn't reduce to the identity. I'm going to say a little more than really needs to be said, but it's worth saying, okay? Because you're going to need to know it. If A has no inverse, then when A is reduced, it's going to have a row of zeros. It's going to be one or the other, okay? If you completely reduce the thing, it can either be reduced to the identity, or when it's reduced, it's going to have a row of zeros. So you want to understand that. And you see matrices that act both ways. Call such a matrix singular. If you randomly generate a bunch of matrices using real numbers, okay, very few of them will end up being singular. Very few of them will end up reducing so that you have a row of zeros, because for a 2 by 2 matrix, that means one row has to be a multiple of the other. And actually, if you generate all the numbers in the matrix completely randomly over the real numbers, it's impossible that any two of the numbers will be the same because there are so many of them. Okay, the probability of getting two numbers the same is 0. In fact, the probability of getting one number to be a given multiple of the other is 0. And particularly, getting one row of a 2 by 2 matrix to be a multiple of the other row is even more impossible. So you would never get a matrix that doesn't reduce down to the identity if you use all real numbers. Okay, there are infinitely many of them, so many that it's impossible for one to be a multiple of the other. Okay, a given multiple of the other. Okay, that's why we call it singular. It's in the universe of matrices rare. Now, this is not rare in applications. In applications, you get singular matrices all the time because you're not randomly generating the numbers. They correspond to something in the real world. And if that thing in the real world behaves in such a way that the matrix is going to be singular, it's going to be singular. Well, that's kind of a circular statement, but I don't want to go any deeper into it than that. Okay. Has an inverse, then we say it's non-singular. And A reduces to the identity matrix I. Okay. Now that's a big deal in this course. Okay. Singular versus non-singular matrices. Matrices with inverses, how do you find inverses? It's not simple. 2 by 2, they're fairly simple. You switch a couple of numbers and a couple of signs. But as soon as you get to 3 by 3, that's not going to work. Then it turns out that the best way to find the inverse of a matrix is to do a Gauss-Jordan reduction. Okay. And I'll just say it now. You don't need to know it. But I'll say also, the matrix you get, if you take the A matrix and augment it by the I matrix, then by Gauss-Jordan reduction, it can be reduced. You take this A matrix, you just do the row operations that reduce this A matrix to the I, and you do those row operations all the way across, including to the I matrix. And what do you get at the end? You get the inverse. Okay. If A doesn't reduce to I, of course, you don't get this. Okay. So that's it. This is a set of equivalent conditions here. If A has an inverse, it's non-singular. If A is non-singular, it has an inverse. If A has an inverse, reduces to the identity. If it reduces the identity, has an inverse, and it's non-singular. If it's non-singular, it reduces to the identity. Every one of these is equivalent to saying all four of them. That's a kind of a neat idea that you kind of want to get into your head, that you can make statements of that nature, because you probably haven't seen that many of them at this point. Now, another important idea is the matrix transpose. Okay, matrix transpose is very simple. Let's take a matrix, and I don't want to use a square matrix right now. Let's say we've got 1, 2, 3, 4, 5, 6. Okay, the transpose of this matrix is the matrix you get if you turn the rows into columns. Okay, of course, then the columns become the rows. The first row becomes the first column. So we have now 1, 2, 3, and then second row becomes a second column. That'll be 4, 5, 6. Okay. Now let's just demonstrate one of the really important properties of the transpose. You won't appreciate this at this point, but late in the course we get into symmetric and orthogonal matrices and Hermitian matrices and unitary matrices. Stuff has very deep applications. Like you write all of quantum mechanics in terms of Hermitian matrices, basically. And I shrug my shoulders at that. I don't have real deep knowledge of that, but I do understand the linear algebra well enough. It's the physics of it that I'm not quite as don't know that quite as well. So I can mention it, but don't ask me to do a lot of explaining of the intricacies of quantum mechanics. Okay. Okay. So anyhow, we have this matrix. Okay. If I multiply this matrix by its transpose, so let's see, I multiply 1, 2, 3, 4, 5, 6 by 1, 2, 3, 4, 5, 6. And notice that by doing the transpose, it doesn't matter what the dimension of your matrix is, its transpose is going to match up for multiplication, because the length of a row is going to be the length of a column. The length of a row of this matrix will be the length of a column of this matrix. And you'll have exactly as many rows as you have columns, since your rows have become the columns. So you're going to be able to do the multiplication. In this case, here we have it. Now, I'm not going to write everything out, but 1, 4 multiplied by the column 1, 4 gives us 1 and 16, which is 17. 1, 4 multiplied by the 2, 5 column gives us 2 and 20, which is 22. 1, 4 multiplied by the 3, 6 gives us 3 and 24, which is 27. 2, 5 times 1, 4 is 2 and 20, which is 22. 2, 5 times 2, 5 is 4 and 25, which is 29. 2, 5 times 3, 6 is 6 and 30, which is 36, making sure, okay? And 3, 6 times 1, 4 is 3 and 24, which is 27. 3, 6 and 2, 5 gives us 6 and 30, which is 36. And 3, 6 and 3, 6 gives us 9 and 36, which is 45. Okay, now I think I probably did that right, because if you notice, this matrix is symmetric. That means that if you divide it in half by the diagonal, what's above the diagonal is a reflection of what's below the diagonal. So you have 22 here, you have 22 here, you have 27 here, you have 27 here, you have 36 here, you have 36 here. So these things kind of join up. This is related to this to this, equal to, and this is equal to this. Okay, this is a symmetric matrix. Which has a lot to do with the ways you can represent the matrix, okay? We have a whole course to go before we get to the implications of this. Okay. And the reason for this is really very simple. Where did this 27 come from? Well, that's the first row, the third column. The first row and the third column matches up the 1, 4 with the 3, 6. Where's this 27 come from? It's the third row and first column of this matrix. So it comes from the third row, 3, 6, and the first column, 1, 4. Well, notice that the 1, 4 and the 3, 6 that make up, that give us this 27 are the same as the 1, 4 and the 3, 6 give us this 27. So no surprise that this process gives us a symmetric matrix. So that for any matrix, A transpose exists, A times A transpose exists, and A times A transpose is symmetric. As I say, this is a big deal. Take my word for it. You'll love it when you get to it. You got to understand it now. Okay, so A transpose is symmetric. There's one more big deal. A transpose equals A transpose A. Okay. A little teaser for the future. For some important matrices or classes of matrices, A times A transpose is the identity matrix. So A transpose equals A inverse. Now you do this over the complex matrices and matrices that have this property, complex values, complex numbers for the entries, and we get to that right at the end of the course. That has a name, that's called a unitary matrix. And unitary matrices are also a big deal with important connections to physics in the real world and the way things behave. Okay, well, you don't need to know that right now, but it's kind of interesting just to think about it. Okay, so that's kind of an introduction to matrix algebra. Okay, matrix algebra is the algebra of matrices. It tells you that you can do things like write the equation matrix A plus matrix X equals matrix B. And you can solve for X. X equals B minus A, just like it would any other equation. You could say that if A X equals B, then A inverse times AX equals A inverse times B. But A inverse times A, matrix multiplication being associative, we could do A inverse times A, we just get the identity matrix times X equals A inverse times B. And the identity matrix times any matrix is just X. That's A inverse B. Now we can't divide by a matrix. Matrix division is not defined. And that's partly because there's maybe more than one matrix you could multiply by A to get B. Okay. And you see a little bit about that where you say that you don't have cancellation in matrix multiplication. I'll let you read about that. In any case, you can't divide by the matrix A, but you can multiply both sides by A inverse and accomplish the same thing, assuming that A is invertible. I'll say if A is non-singular. I.e. invertible which, if you remember from just a few minutes ago, means if you reduce it, row reduce it, you can go row reduce it to the identity using the row operations, Gauss-Jordan row operations. Okay. Okay, well, take that as an introduction to section 2.2. And, you know, think about the things that we said here. Then work the homework. If you work the homework before you look at this video, go ahead. But look at the video after you work the homework, you get a little different perspective.